Hello everyone. Today is December 22 and that means we are ready to open a new problem from lead code for our coding advent calendar. Today's problem is hard and I need to spend some time to try to tell you how to solve it efficiently. So take patience and let's start. Here is today's problem. Sum of distances in tree. And this problem is marked as hard. There is an indirect connected tree with n nodes labeled from 0 to n-1 and n-1 edges. You're given an integer n and an array edges where hi equal to a, b array indicates that there is a edge between nodes A and B in a tree. Return an array answer of length n, where answer I is the sum of distances between node I in the tree and all other nodes. Here is an example. This is a tree. 0, 1, 2, 3, 4, 5. This tree is built by these edges. So there is an edge between 0 and 1, 0 and 2, 2, 3, 2, 4, 2, 5. So we built our tree. And an output should be like this. For node 0, this is position 0, sum of distances is 1, 2, 3, 4, 5, 6, 7, 8, right? Because the distance between a root and node 5 is 2, right? 2 edges. Okay. So this is very interesting problem and let's try to solve it. So in order to demonstrate you the solution, I need to have some space in comments. So let me draw some, I actually have one. Let me draw predefined tree here, not to take much time. So there is a tree here. And how can we solve this problem? We can actually, for each node, we can go through all nodes, right? It's actually a graph, right? So for each concrete node we can go through all connections and calculate the answer, the result individually every time. So for every node we need to traverse the whole graph, the whole tree. This is not effective, right? How can we make this more effective? Let's consider two parts of this tree. So let's imagine we split this tree in two parts. There is a x part and y part, so two parts of tree. And also imagine that we have calculated the result for x subtree and y subtree. So imagine we have it. Now we are going to join these trees. How should we adjust results for nodes for these roots x and y to reflect this join of these subtrees? So the formula, if we have result for x and y, so for x the result be like this: result x equal to So we take the previous result, so it will be plus equal. So we need to add result for y, right, plus number of nodes in y sub 3. Why do we need this? Because result y stores the correct answer for y sub 3, where this is the root we are dealing with. When we add a connection between x and y, the result of x should be increased by the correct number of results, so the correct result for y plus the count of y nodes, because every single node has length plus 1 to x, right? Because we have this connection. That means this node have length 1, this node has length 2 to x, it had length 1 to y, and so on. Every single node in this subtree will have increased length to node x. So now we have some formula that can help us to reduce amount of computations that we need to solve the problem. So let's use this formula, but before we do this, we need to do some pre-computations, right? Because we need to do some basics to which this formula should be applied. And in order to do this, we will calculate the correct result for the root of the tree. Once we have it, we can use this formula to calculate everything else in a tree. So let's do this. So let's first define our array, which will be our result. And as we saw, in the formula there is an array count, right? So for each value in an array, for each node we also will store something called count. So let's define it. And we also do not have a graph tree, which is basically a graph. We only have information about the number of nodes and the edges. So we need to define our graph. Since our nodes are numbers from 0 to n, instead of dictionary, which we used previously in our solutions, we will use an array of length n. That means we can have fast access to any node in this data structure by using just address in an array instead of dictionary in previous examples. So each of these nodes in this array, which will have a list of connections, right? So it will be list of integers and array of these lists we have. A graph. Okay. Oh yeah, sorry. This. Let's put it here. Let's put it as private variables of this solution class. And let's do the following. Let's use something that we used before. Let's create a function called buildGraph. To build the graph, we need to pass the number of nodes and edges, our input data. We also need to allocate these two arrays with the number of our nodes, right? Okay, done. Let's do this. Let's create a function that will return us this graph. And this function should look like this. List int array graph, go to view, list int array of length n. Let's allocate this array with empty lists. And let's go through edges. This is pretty much the same that we used in previous examples. So we add connection, for example, to node 1 from node 0 perspective, and we add connection to node 0 from node 1 perspective. So it's bidirectional. And our graph here is completed, so we return it. Okay, this function is ready. What are we going to do next? We need to calculate our result for a root. We will do the following. We will use post-order traversal to do this, and when we do this post-order traversal, when we leave some node, so some child to parent, right, we need to add new we need to add count of this child to parent, and we also need to add this count to the result, and plus we need to add this result to this result. So for example, if we go from node 3 to node 1, when we do our post-order traversal, so the number of nodes here is 1, the number of lengths is 0, because this node does not have any child nodes. So when we go here, we add 1 to count here. So this node count has 1, and plus 1 it has 2. And we also count this edge. So we take 0 as a result from here and add 1 because we have only one node here. Let's do it like from this perspective. When we go from 2 to 0, when we do our post-order traversal, how should we update our results and count arrays for index 0? For index 0, we have already some calculations because we have left part of the tree, so it stores some value. So the count with index 0 should be increased by the count of this node, where this node stores the count of all subtrees plus 1 plus itself, right? So we need to increment the count for index 0 with all this, right? And for result part, for result array and index 0, we need to do the following. We need to increase it by the result from here plus count of from here, from this node, because every single node, as we discussed, has lengths of connections increased by 1 if we are talking about distance to this concrete node. I hope this you understood this. So let's do this. Let's do post-order traversal. This mechanism is well written in the internet, so you can review your knowledge about this. We will not spend a lot of time. And what we should do next? We have our graph, which is actually a graph. So from this perspective, we don't know who is a child, who is a parent, right? But we look at this graph as on a tree, right? So from our perspective, it has child nodes and parent nodes. To reflect this while we do traversal, we need to block backward connection from child to parent, because we don't want to traverse back, right? So when we go from parent to child, we need to store this parent somewhere, and when we go through connections from this node, we need to skip this connection back, right? We need to take only connections to other nodes. Since every node has only one parent, we can do this. So if child equal to parent, we need to just skip it. If it's not, we do our post-order traversal. We go deeper into recursion calls. So we pass this child from this node as a parent, and we set this node as a parent to recursion call. And as we discussed, when we done with calculations for children, we need to update a parent, right? So count for node should be incremented by count of child we just calculated, and result of this node, which is a parent, should be increased by a result of child plus count of child, right? We discussed before why we need this argument, because when we consider parent, every single connection in child subtree increased by 1. So we need to add this count here. Okay, using this algorithm, we are ready with calculating the value for root of tree. All other values will be not valid because they are calculated based on only subtree, right? And we need to go through them again and consider connection between parent, which is root, which has correct value, and this child, which has correct value only for its subtree, and we should update its value using formula. We have this here, like here we calculated y correctly, but x is correct only for its subtree, for x subtree. And now, when we have correct value here, we can restore this connection back and update this x using this y, right? Using the same formula. So we need to so we need to do something similar again. Okay, what we are going to do? We will go through all connections for this graph. We for this node, right? We also need to skip backward connection. And we need to use the formula here to update its value. So result of child equal to result of node minus count of child plus n and minus count of child. Is that correct? Yes, and this is correct because this is correct because the number of connections to the child node um, should be the count of connections to parent nodes minus the count of child nodes, because all child nodes from this subtree will have connections one less, right? Because we're going here down, so all child nodes will have less connections if we reflect it here, right? So to y, this x has connection length 2, to this x has connection 1, right? So 1 less. That's why we decrement this one. But from other hand, all nodes from the other side have connections one more. So each node has connection plus 1. So we need to so the count of these connections, so the count of these nodes S is n minus count from here. So the formula should look like this. And we also need to call this recursively to all child nodes. Okay, and what left? We need to call this. We will call this for root node, which is 0, and we need to pass some parent, since we should skip backward connection for a root node because it doesn't have any parent. We will send a number which does not exist in our array, which is -1, for example. We can use any negative value here. Then when we calculated the value for a root node, we need to trigger this function. And again, starting from the root node, which is 0, send parent as -1, and we also need n there. And then our result array should be ready, except for one interesting thing. Well, when we are calculating count, we are calculating it based on childs of current node. We does not count this node itself. So we need to initialize this count array with ones, not with zeros, because every node has a count of itself, which is 1. Okay. Okay, all these cases are accepted. Let's submit our solution and check. Okay, it is accepted, but I don't have this badge. It is actually 11:34 my time. Probably I was not able to be on time with our coding advent calendar. Anyways, our solution beats 85% in CPU of all accepted solutions. and we don't have many solutions for this problem, right? Because this graph looks weird. Okay, this solution, okay, complexity of this algorithm. It has big O of n time complexity and big O of n memory consumption. Why big O of n? Because we need to do two post-order traversals for this graph, which means we need to visit every node once per every traversal, and we also store these two arrays as part of our solution, which are lengths of length n. That's it. That was really interesting problem, and it was actually hard. If you think you not totally understand how this solution works, don't hesitate to ask me in comments. I will try to help you. See you tomorrow.